Okay, welcome back everyone. So today we are just going to be doing a probably our last video in the series, but basically I'm making this video to show you all the other, or some of the other things that I, have programmed, not just coding the programs, but actually showing you the projects that I've been working on. But before that, I think we'll just quickly do one more thing, and we're just going to solve a basic differential equation and graph the solution, okay? And basically this is simply just going to take the shape, we'll call this constant here tau, not to be not to be uh, not to be uh, how do I word this, not to be misconstrained with the tau constant, or the irrational number tau, which is 2 times pi essentially. So we have dy dx. So this is going to be our structure, by the way, and it's going to be in the form, let's say, we'll call this u of t minus k times y. And we can just call, and we'll actually call y, so y of t, right? It's, in terms of time. Oh, and by the way, I actually just need an eraser. This should be with respect to time, right? And we'll have this step. We'll have a step function here. Okay. Okay. And we'll set our tau variable in this case to be, we'll just call it 2, and our k variable, we'll just do plus k. We can do minus k. And our k variable can be equal to, well, let's just say like 5. Okay. So now our new form is, and let's solve for dy dx, and the computer is going to integrate both sides for us. So we'll divide by 2 to isolate our dy dt, and we'll plug in our values. We have u of t minus 5 y of t over, well, over 2. Simple enough, right? Okay, so this is what we want to look at. So let's go back here and let's see how we would do this. Well, let's see. So I've basically imported matplot.lib to matplot.lib and pyplot as plt to graph these functions, the solutions, and I imported Odient from Scrippy from SciPy integrate. Okay. So let's do this. Alright, I'm not going to bother with the title. So let's define a function, and this is going to be a function that models basically our differential equation here. Okay. So let's define a function. We'll call it model function. We'll call it model function. Okay. And we want to take in the inputs y and t. Okay. And we'll just simply, actually, we'll have a step function so that such that t is, let's say t is less than, if t is less than 5, u equals 0, and t is greater than or equal to 5, u equals 1. Normally you'll get it in kind of like a word problem, but I'll just directly have it like that. So we can have like an if-else statement, I suppose. Oh, I don't know. Sorry about that. So essentially, we can have an if statement. So if t is less than 5, we'll say u equals, in this case u equals it was u is equal to 0, right? And then else, of course, u equals 1. Okay, simple enough. And now we just return our function. So return our function, and that's just going to be, I'll put this over here. That should simply be, well, this here, or we're focusing on this. And since these, we haven't defined these as functions, we're just going to have u and y, and that's why we have our input t, because they're all in terms of t, right? T is, in this case, the independent variable, and y and u are the dependent variables. Okay, all over 2, so u minus 5y over all over 2. Oops. U minus, okay, u minus 5y over 2. And actually, I want to put this in a variable, and we'll call it dy dt. So dy dt equals this, right? Okay. And now we want to actually have a initial. We need an initial value here. Let's see. Yeah, we need an initial value. In this case, we only need 1. Okay, so why not? Let's just say this is simply equal to 6. I mean, we can have the user input value. So we can have integer input. Okay, so initial value. Oh, sorry, initial condition. Initial condition. Okay. Why not? So we can say why not equals. Okay, that works, I guess. And then we want our time interval, and essentially we'll call this t, and we'll call t. It's actually worded with linspace, so linspace we'll have it from 0 to 20. Okay, that's our x-axis in this case. And finally, we want to have our solution, so we'll call this our y. Okay, and basically the command for this, the syntax is just odient, and we plug in all of those things here. So we can plug in our y, and then our y naught, and our time. Okay. And finally, we should simply be able to graph this, okay? So we can just graph it. And basically, we can just do plt dot plot. And obviously, our x-axis is our time, and our solution, our y. Right? Pretty simple. Okay, nothing too special. And actually, yeah, we can have this as a red line. Yeah, I'll just do blue line, and let's say it's just, I don't know, maybe like kind of dotted line, because why not? And we'll have our line width equal to 2, because this is going to be the only plot. Okay, that should be enough for that. Oh, and maybe we can have our, I don't know, label equals, I don't know, maybe, well, we'll call this like a graph of u of t, oops, a graph of u of t minus y of t, well, minus 5 times y of t. You know, we'll just call it our y of t graph, okay? Because, yeah, that's our solution here. And, yeah. Okay, simple as that. Now, shouldn't be anything too special. We can do plt.legend and take in those values. Let's see if this works here. Oh, syntax error. Oh, I see what I've done. I've gone with my intuition, haven't I? Okay. So input initial condition. Oh, linspace. Is it np.linspace? I'm actually not sure. Y is not defined. Okay. Should be just fine. Oh, I see what I've done. Yeah. Let's see. Oh, okay. Just need to put in our dy/dt, right? Oh, dy/dt. Okay. Put on hold for a second. Okay, we're back, and essentially just the model made a silly mistake, so just have to input the model instead. Should work fine now. Oh, invalid syntax. This might be a glitch, I'm not sure, because line went. Oh, okay, no comma here. There it is. There's our very peculiar graph, I must say. So yeah, that should work, right? Should be correct. I'm just gonna check everything. Okay, should be fine. And of course, I inputted initial condition of 5, right? So essentially, it's going to be our initial value here. And as you can see, that's our step function at work there. So pretty interesting, pretty interesting. And yeah, that's our solution to our graph. So now I can show you some of my other programs. I want to keep this video fairly concise, okay? So let's go over to Diffie-Q. And these are basically some of the differential equations that I've solved. So obviously our imports, here's a brief overview, solving differential equations to find the differential equation. This is what we've done. This is an even more basic differential equation, right? And give one or more initial conditions. So here I allow the user to input an initial condition. Okay. And over here we have our time interval, and this number here, I think it's initialized at 50, but the greater the number, obviously the longer computing time, and the smoother the line. Okay. Let me just make sure our legend worked. Yeah, our legend worked. Yeah. Okay, it's all fine. Graph legend. Okay. And here I basically solved multiple differential equations at the same time. In this case, 3, where our k constant here actually varies, and this is the syntax for that in this case. And here I just plotted this, and the reason this is here is it basically picks the best location for the legend, but I think in this case Jupyter Notebook picks the best location automatically, so it's kind of unnecessary. I just added that there because just in case, maybe it might help. And obviously our time axis, oh, I forgot to add the x label and y label. I mean, it's not necessary, but we can add it anyway. That's simply just the syntax for that is just I'm going to add this up here. X label equals, actually we can just write it like this, so x label equals, obviously we'll just call it our time axis, and we can set the font size equals 13, and then we can copy and paste. So f of t, sorry, y of t, axis, and then our font size 13, and yep, we could also have a title. So, oh yeah, plt, that's important. So plt dot title, and we can simply call this maybe like first order differential equation solution. We'll have like font size to maybe 14 or 15, font size equals 15, and this, and there we go. We have a title, we have a nice X label and Y label. Oh, where did the Y label go? Okay, let me just swap that out. Yep, there we go. So X label and Y label, yeah, pretty nice. So there we go. I'm just gonna head back to here. Okay, so here I made another one. It was just as simple, just same process, just for practice. Here's a similar one that we did, not the same of course. It's also related to a step function. Okay, and yep. So let's continue. And here is a little bit something a bit more complicated. It essentially utilizes vectors here, and we define the function model as usual. And in this case, we use z, where our x section and our y. This is basically graphing two differential equations at the same time. And our x label here, or not our x label, our I just simply called this because it's just going to be dx dt on this case. So that's our first differential equation, and I just set that to be the first term in the list, and y in this case dy dt is the second term in the list. And basically this problem, it's just 3 times e to the minus t, so that's dx dt, and dy dt is just 3 minus y of t. And yeah, I returned them as a tuple. Okay, as a two-tuple, and I had initial value, and we need 2 initial values, right? Since it's a second order differential equation. So the more times you integrate, the more initial conditions, sorry. And our t in this case, and p dot in space from 0 to 20 again. And here we just simply solve this. And here's just some vector notation. This simply means, basically this outputted z outputted a matrix, and we just wanted to set x equal to that matrix, so the first column in the matrix and all of the rows in the first column. Okay, and so essentially just an entire column. Okay, yeah, so entire column, yeah, basically, and here's just the second row, and I'll just get rid of this for a second and show you what I mean. So if we just run this, yeah, this is what I mean here. So there's this column, first column, and the second column. I wanted to separate them. Okay, that's exactly what I did. And then all I did was just plot them separately. Okay, and in this case, the legend, the notation for the legend is a bit different, since we have to have it as a list, as a tuple, or sorry, as a list, right? And you just have to have the list in order, right? So whichever plot you graph first, you have to have that specific solution in the first term here. Okay, so there you go. If you just run this, yeah, something is quite peculiar here. That's interesting. Oh yeah, this essentially, because the problem was asking whether these two differential equations are equal or not, and obviously this proves that they are, so it solved the problem. Here's something on a similar line, on a similar note, except it's a bit more complicated because it includes the step function and 2 differential equations at the same time. So I'm not going to go through it all. That's the output here, so they're not equivalent. Okay, and I actually have a lot more to show, but this video is already getting fairly long. Here I'll quickly scroll through my calculus numbers. This here. Yeah, I've only been coding for about a week now, so yeah. So here was my Taylor series for cosine of x, right? So that's where I made it, came up with it, and here's some first time I was introduced to plotting and PLT in MATLAB.lib. Here's just our integral calculator, all of this cool stuff, right? Here's just some practice. I was just practicing differentiation. And yeah, there's a bit more, right? But I hope you enjoyed. Those were the juicy bits, and I'll see you in the next video. Goodbye.